So far we have manipulation, legipulation, and beakpulation, so a prize to the person who invents the next word. And I'd like to introduce our next speaker, Anibal Ollero. He is a professor at University of Sevilla in Spain, and he's going to continue the aerial robotics theme.
Thank you, Kevin.
Please join me in welcoming.
Thank you for inviting me to this very nice single track event. So thank you to Taming and Stefano. So yeah, I'm going to talk about bioinspired and soft aerial robotics. So that means that we have been starting 25 years in different kind of aerial robots. I mean, starting beginning of this century, these results are in European projects that I coordinated. So I started by the beginning of this century, and then we developed this helicopter system that cooperate with others in the detection and monitoring of forest fires, at the same time coordinated control and so on. Then we were to the integration with the environment, with the structure, ground structure, and also to some application like the transportation of a load between 3 helicopters. This was difficult. This was collaboration mainly with the Technical University of Berlin, with at that time was my friend Konstantin Kondak. Then we went to aerial manipulation. Aerial manipulation means flying and manipulate at the same time. And we developed in the ARCAS project the first general purpose aerial manipulation system. And then later we apply industrially, not in the lab, but industrially, in the industry for the testing of the wall depth by using ultrasonic sensor. Then we went to manipulate with 2 arms, and finally in the last year we had several experiments on the inspection of electrical lights, not only flying, but perching on the tether and then rolling over the tether, so combining locomotion modalities to save energy. But then the main problem of all this, I would say 2. First is the safety, very important, the safety. It is very difficult to get permission to fly, but also because it's unsafe in many cases. And the second is the flying endurance and range, which is related to the energy, of course. And then, okay, we have more problems in some kind of locomotion than in others. Of course, we have to, it is possible to land and roll and so on. But anyway, these 2 problems are very important in aerial robotics. Then we went to bioinspired for aerial robotics that for us means flapping wing also. Flapping wings and other mechanisms that I will try to summarize. But at the same time, we see that for some parameters like the agility and so on, it could be good to have multi-rotor system. But we wanted to have multi-rotor system interacting with people. So that means soft. We have not in the nature, only at the, let's say, nanoscale for the bacteria, this full rotation of the propellers. So I cannot say that this talk is fully bioinspired. Then we went to this advanced grant of the European Research Council, which is Griffin, and we developed all these methods for the flapping wing, including the design, the modeling, actuation, control, perception and autonomy, and also the perching and manipulation that I will try to summarize some of these results in this talk. So first, let me go to the fly. Not only flapping, but we also added some components to have more payload and to have more energy efficiency, imitating the birds. Like, for example, this actuation in the tip of the wings, or also the passive joints and so on. And then we want to compute how is the energy efficiency. So we wanted to do that, so you can see flying outdoor wing is critical, it's very important. So we did in many experiments, and you can see some comparison with the multirotor. There is no possible comparison with multirotor, with always wing, but people can take care about the comparison with the fixed wing. So you can see some numbers there, so we put some propellers, and we fly with this system and compare flapping wing with gliding is very important, ability to glide. But of course, you need more intelligence to glide, sensing the wing and so on. Then we want to also to put intelligence on board. That means we use event cameras. Event cameras were very important due to the properties, also bioinspired. So that means that we were able to close the loop, visual servoing, to guide the system, but also to detect and avoid obstacles by using this event camera. So it was, again, the first doing that. Then we went to the perching. So this is much more difficult than Pershing with the multi-rotor system. You can see the oscillations of the variable here. This is very difficult to control and to cancel the perturbations. So we needed to compensate in the last meter by using this leg without degree of freedom to compensate by using visual servoing. And then in parallel, we developed Bioinspired cloth that I have no time to present here. We wanted to have not only that, but we wanted to have also manipulation. So we developed different beaks, manipulation sensing with the beak, but also manipulation while maintaining the equilibrium, which is difficult. We put some manipulator, very light manipulator on board the birds. And finally, we put two arms to manipulate, being able, for example, to take sample of stems and leaves. And finally, the cooperative manipulation between two. So one person near the other and pass some samples. So this is some of the topic that we have been working, and I need to pass immediately to the soft multi-rotor system, which is the second part. So here the critical aspects are related to combine the flexibility of the body of the arm and the variable stress of these arms with the propellers and being able to control. The design was very important, combining in the design the mechanical property, the resistance with the propellers and the aerodynamic properties. We have to combine both of them, and of course we have to control. It was difficult to control because, as I mentioned, the deformation with different stress in different parts, and then the vector of the propeller needs to be compensated, taking into account the model of the deformation of the arms. So everything is model-based. And finally, we were able to control modeling, but with relatively very simple controller, but good modeling tools. This is what we did. And then we passed to the propulsion alternative. Two possibilities. One is to have flexible propellers. So you can see flexible propellers here. So you can put the stick, you can put the finger, and we can compute this, how this behaves after the collision, let's say collision. At the same time, more efficient in many cases, we put some embedded ducted fans in the arms to have in this way the ability to land, for example, adapting the body. These are the two kinds of systems that we use now for propulsion. We went more in the details how to model these flexible arms, how to take into account the variable stiffness in different continuum models. We try to integrate the behavior of this system in all these continuous models, and we compute forces and torques to be applied in the dynamic model. And then we are able to optimize the system, selecting, for example, giving the velocity this beta angle that you can see in the figure to select that better behavior. And then we went to two typical things that you will see. For example, the first, for sure, in the presentation of Antonio Franchi, that will be the fully actuated system that are able to exert forces in any direction and don't need to incline the body to move. So we did with the soft systems, and at the same time, we did the Pershing. Pershing means many kinds of different Pershing with different prototypes that you have seen in the previous video. Again, we have to take, obviously, into account for the Pershing the aerodynamic effect, and particularly the ground effect. Obviously, the force that you have to exert depends on the ground effect, and also the Coanda effect. So we model, and finally we are able to have this Pershing in different kind and different surfaces, adapting the body to different surfaces, which is not trivial. Okay, I promised myself to be in the 10 minutes. So I will be in the 10 minutes, but still I have some comments to have as conclusions. Conclusion means first, for the bio-inspired system, the flapping wing, I think that we did for safe and efficient flight and Pershing and manipulation, but we need to solve some challenges. Dealing, very important, flying with the optimal use of the wing. Not only reject the wing perturbation, as we typically do in aerial robotics, we have to use the wing to move the body as the birds do. And also, we have to improve the manipulation capabilities. The second, in the soft part of the multi-rotor system, We have to increase the safety. And so we want to have piercing on the body of the people, interact physically with the people piercing on the body without hurting them. And then this is obviously one of the challenges. And the other are the increase of the intelligence and the range and time of flight. So just to conclude, my last comment, in all that I have presented, there is a lot of physical models, kinematic, dynamic, aerodynamics, material science model. But at the moment, we did not apply, so the 10 minutes, we did not apply the artificial intelligence learning, but I hope that with the help of many of you that I have been interacting and I have been attending the very nice presentation, we will be able to do. Thank you very much for your attention.
Thank you, Anibal. Questions from the audience?
Thanks a lot for the nice presentation. As someone that works with multi-rotors, it's very nice to see that with the soft designs, it makes me feel a bit, how to say, maybe encouraged in the presence of multi-rotors. So I want to ask you, what is the main challenge for these systems to be reliable and, how to say, be more the main trend in multi-rotors?
Okay, reliability is always a main problem. We have to demonstrate that this system can be safe, for example, landing on the body, touching the person to measure some parameters, like, for example, the blood pressure, and have to perform this kind of interactions. So this is a very important physical interaction that nobody did. I think that this is possible. This is possible, and we can demonstrate this kind of properties. Of course, we still have to be efficient from the point of view of the energy, which is, by the way, not trivial. Being at the same time very efficient and soft is not always trivial. So we will try to do, but I think that there are many challenges that depend on the properties of the material and how we control the material to adapt as the animals do. So bio-inspiration again. We need also learning. Yeah, we need learning.
Okay, please join me in thanking Anibal one more time.
Thank you.